Hello everyone, my name is Afan Abbas and I am an AI science instructor. I have around 3 years of experience in the field of artificial intelligence, machine learning, deep learning and computer vision. I have 3 publications in the same domain. Currently I am working as an AI sciences engineer and the topic I am assigned is graph neural networks. My own research these days is also graph neural networks. It's a very hot topic and it's gaining very much popularity these days. So let's get started on it. Our outline will be we will be looking at graph neural network basics, computer vision applications, and Python code, PyTorch code basically. The recent success of neural networks has boosted research on pattern recognition and machine learning and data mining. Machine learning tasks like object detection, image processing, machine translation, speech recognition have been given new life with end-to-end deep learning paradigms like CNN, RNNs, and autoencoders. Deep learning is good at capturing information of Euclidean data, such as images, texts, and videos. But what about applications where data is generated from non-Euclidean sources, such as graphs or 3D surfaces, 3D images? That's the place where GNN comes into picture. Graph neural networks comes into pictures. We'll be looking at the graph neural networks and its implementation in this tutorial. So let's get started. CNN. CNN stands for Convolutional Neural Networks and it basically uses Euclidean space. And graph neural network use non-Euclidean space. And now we will take a look what is Euclidean and what is non-Euclidean space. While Euclidean geometry seeks for understanding the geometry of flat and two-dimensional surfaces, like we deal with two-dimensional surfaces such as images, videos, and texts. But rather than curved or rather than flat surfaces. We use curved surfaces when we deal with non-Euclidean geometry. Although Euclidean geometry is useful in many fields, in some cases non-Euclidean geometry may be more useful. These days non-Euclidean surfaces geometries are also being used in the field, so that's why there is an emergence and there is a need for graph neural networks. What is computer vision? Basically, computer vision is how a computer sees an image, how it remembers what the color is, what the orientation of an image is, what is it detecting. Computer vision is a field of artificial intelligence that trains computer to interpret and understand the visual world, like it understands, like where is a car, where is a dog, where is an object located in the image, its coordinates, its tracking, detection, and counting. These things all come into computer vision domain. Graph convolutional neural networks. They are basically advancement of convolutional neural networks in the graph domains. When we use two-dimensional space, we use convolutional neural networks, and when it comes towards three-dimensional spaces, we come towards graph convolutional neural networks. Similarly, the neural network architecture is almost the same as we use in deep learning, but now in case of graph, there is a structure which is like graph. Like you can see in the image, there are graphs in the input, output, and the hidden neurons. And there is ReLU activation functions between them. What is ReLU? It is rectified linear unit, and it brings non-linearity to the data, and it's the most widely used activation function used in computer vision domain and machine learning deep learning domain these days. Let's move towards the PyTorch code. So here's the code for the graph neural networks. Let's get started. From torch geometric dataset, import planetoid. Planetoid is basically a dataset and it has further 3 datasets in it, which are namely Cora, Sightseer, and PubMed. Import torch. What we are doing here, we are importing torch, like it's basically a deep learning library used for implementing deep learning models, and it's most widely used these days. Previously TensorFlow was being used the most widely, but currently PyTorch is being most widely used. Import torch functional as f. For functional is basically for convolutional functions, pooling functions, and similar type of functions. From torgeometric.nn import message passing, we can import data from here, like we can import images, videos, text, like such kind of data from here, which is by default prepared in it. From torgeometric utils, import add self loops and degrees. Now let's take a look on what are add self loops and what are degrees. Add a self loop to every node in the given graph by edge index. What it is doing, it is having a self loop to every node in the graph. And degree computes the unweighted degree of given one-dimensional index or a tensor. Import network as NX. Basically, it understands the complex structures which graph neural networks use, like 3D images, curved surfaces, and all that. Import numpy as NP. We can give any name like MP, numpy, NP, or any, but when we will call that function, we will have to use the same. NumPy offers comprehensive mathematical functions like matrix multiplication, addition, division, and all such kind of mathematical relationships. Import matplotlib.py plot as PLT. It is basically for visualization, like how the graphs are being formed, how the images are drawn, and all the kind of visualizations are being done mostly from matplotlib library. Here we were importing the libraries. Now let's move towards the further code. So here is a class convolutional neural network message passing. Define any initialize self, in channels, out channel. Basically these are, we are passing parameters. Superclass is formed after that. Superclass is what is a superclass? It basically have all the attributes of the parent class. Whatever it is following, it adds all the attributes in it. Self line torch.nn, in channels, out channel, but we are again passing parameters over here. Define forward self, x, and edge index. What we are doing for in the first step, we are adding self loops to it. Edge index is equal to add self loops. Edge index num node is equal to x dot size 0. It on the first index value. It means it is taking the first index value. Step 2 is multiply with the weights. What we are doing, each weight is assigned a random weight. This is being done in this line. Each value is being assigned a random weight. It is being multiplied with a random weight. Calculating normalization. Normalization or standardization are basically terms which present our data in the same format. Like, let's say I can give you an example. There is a data and it lies between 1000 domain, like there is a price of a house. It is, let's say it is $1000, or a rent of a house, it is $1000, and one thing is number of rooms in a house, that will be 2, 3, 4, 5. But to have this is in all in the same domain, we use normalization. So it rearranges data into -1 to 1 or 0 to 1. This range, it brings the data to a same range for all the data. Row column is equal to edge index. Degree is equal to row x dot size. Data type is equal to x dot data type. D type stands for data type. Over here it is taking the power. Power minus 0.5 means half power is being taken. And what it is returning, self-propagate, index size x is equal to x, and norm is equal to norm. What it is doing, it's propagating the embeddings to the next layer. Propagate means decide whether a log should be propagated to the log parent. By default, its value is set as true. Over here you can see it is being arranging the data into range of -1 to 1, which I was telling you previously that what is the range of the data we are going to use. Class net torch.nn module. You can see that the net is written with the capital letter. It is starting with the capital letter, and this is Python's format for a class. Whenever we use a class, its name must be written as capital. So what we are defining it, initializing itself, dataset. Again we are taking as a superclass. I already told you that superclass is having all the attributes of its parent class. This is convolutional. GCN stands for graph convolutional network, which I saw you a diagram as well and explain a bit over there. This is a function which is named as forward, self, and data. X, edge index, data dot x, data dot add index. We are passing parameters over here. I already told you what is ReLU. ReLU is rectified linear unit. Let's take a look at its diagram as well. This is rectified linear unit. It brings non-linearity to the data. For 0, its value is less than 0. Its value is 0 for less than 0. Like in negative values, all its result will be 0. Its value is x for x is greater than 0. It means that at 1 its value will be 1, on 2 its value will be 2, and so on. Dropout. Dropout is a regularization technique that randomly switches off some neurons in order to prevent overfitting. Now, what is overfitting? Overfitting basically is like the model performs good on training data, but it doesn't perform well on the testing data. So, this is overfitting, and we randomly switch off some nodes so that the network cannot get all the weights and biases. It will randomly remove some neurons, and in this way, we can prevent overfitting. Let me show a diagram which will explain this procedure. Take a look. The first diagram in A point, it's written standard neural network. By applying at point B, it's written by applying dropout. You can see the crosses are being drawn over there, which means that these neurons are being randomly dropped out. So in this way, we can prevent overfitting. What is softmax? Softmax is basically an activation function. It gives the probability of occurrence of a class. Let's say we are predicting cars, buses, and trucks. So let's say all the probabilities for these classes will be given, and the highest probability will be on the top, and it will be the most accurate measure for that. Let me show you a pictorial representation of that. Softmax is a mathematical function that converts a vector of numbers into a vector of probabilities. I already told you it will give the result in the form of probabilities. On the right hand side, you can see 0.9. It is the most highest value for the probability in this case, and it will predict the class as this one. The class which is considered with this 0.9, the answer will be given as that. Let's say it is for a car. Its probability is giving that 0.9% chances are there for that it is a car, and for bottom there 0.1 and 0.0. It means they are having less probability of their occurrence. There is a function again, define plot dataset, edges raw dataset dot data edge index dot numpy, and for that further edges and zip. What is zip? Zip is basically makes a tuple in from a list given. It forms a tuple from them. Labels dataset dot data dot y numpy. Here it is making a list of range. What is list? List is basically in Python, list is and arrays are same. We represent them by square brackets, and they are represented with commas, and if they are any string, we wrote it in inverted commas. We can write single inverted commas, or we can write double inverted comma. Both will work. Plot 111, it shows that it will be the first image of the first side. Let's say if it is given 112, it will be the second image. For 111, it means that it is the first image on the left hand side, and that's why we are using 111. Options: node size 30 and width 0.2. These are given as the hyperparameters. Like we are fine tuning the parameters over here to get good results. After that, we are drawing a map, which is C map, stands for color map. Font size we have taken bold, and double star option means any of the parameters can come over here. If we use double star, it means any options can come over here. It can take any value. PLT show will plot the graph. Now here in this function, we are doing some prediction. If train over here, it will do prediction on the train data. Otherwise, it will do prediction on the test data. In the else case, we are doing prediction on the test data set. In the next function, there is a POC which range from 100. It means it will have 100 forward and backward passes. Model train, it will do the training of the model. What is training? It is the choosing the best number of parameters weights for the model. Training means choosing the best number of weights for the model. Optimizer 0 grad sets the gradients of all optimized tensors to 0. All the optimizers are set to 0 in this case. Output model data loss. Loss is what is actual output minus the model output. What is the difference is basically the loss. What is loss backward? When we call loss backward, the whole graph is differentiated. What means differentiation is being done with respect to the loss. Optimizer step makes the optimizer iterate over all the parameters. And over here we are printing the POC, loss, train accuracy and test accuracies. This all is for the plotting. Like for the train accuracies, we use label as train accuracy. For test accuracies, we use label as validation accuracy. X label is equal to epoch, Y label is equal to accuracy, legend is up on location is on the upper right, and plot show, plt dot show. This is the name of a dataset, which I told that the three datasets are being considered in planetoid dataset, which is Cora. One is Cora, one is Siteser, and what is PubMed. One is PubMed. Over here, it is using device as CUDA or CPU. CUDA is when we are having a GPU on our system, it is CUDA. Else we use a CPU. If there is processing power is not needed, much processing power is not needed, that code can work on CPU. But if it is heavy processing, like we have to run number of POCs, data size is huge, we use CUDA. And we will take a look on Google Colab now, and it has a virtual CUDA or virtual GPU for us, and we can train our deep learning models, huge deep learning models over there without having a physical GPU installed on our system. Optimizer, Torch, Optim, Atom. Atom is basically an optimizer. It has the best features of ADA grid and stochastic gradient descent, ADA grid and RMS prop. Its learning rate is mostly selected as 0.01. What is learning rate? How fast the system adopts to the changing data is known as learning rate. Weight decay is like in the first, the weight is being given with huge values, and after that, when it starts to train, it gives small values. Like there is learning, one thing is learning rate decay. In that case, learning rates become small after specific epochs, or we said that after this much accuracy we have got this much accuracy, after that learning rate should stop. Same as the weight decay. Weight decay over here, what happens, like it drops the weights to a specific value, small values, after the initial value, huge values taken in the start. So we are done with the code. Now let's run this code, and I'll show you the results, and we'll take a look at how that Google Colab works. We'll have an intro of how Google Colab works. Number one, I have cloned the repository. How we do that? First of all, we have to put exclamation get clone and then the HTTP address given over there in the bar of the GitHub code. We will write get clone HTTP and the address, and we'll run it. It will clone the repository. It will take a few seconds. Yes, we are done. After that, you have to copy paste the same command in order to mount the drive. What is being done over here? We mount our drive. We are link our G drive with our Google Colab, and we can import our dataset over there. Connect to Google Drive. Allow. Okay, now what we will do now, we will change the directory. We will put this percentage sign cd and where the main code is written. Let me show you. This main. What I'll do, I'll right click, copy path, I'll paste over here in front of percentage cd and I'll run it. Now there is a package to be installed. How we install a package? Exclamation mark pip install torch scatter. We need to install torch scatter, so we have written its name. Isn't it easy? And it's great that we can use GPU over here without having a physical GPU installed in our system. It has installed the torch scatter package, but it needs torch geometric as well. So what we will do, I'll change this line of code and it will install torch geometric as well. Now it's giving error for torch sparse. Let's install that. It's doing some pre-processing now. Our package has installed successfully. Now it started training. There were total 100 epoch as we saw epoch in the video in the tutorial, as we saw in the code, and loss is this much. Accuracy is 1, which is complete accuracy. The model has trained very well and it has shown a great accuracy. Test accuracy is, it was train accuracy and test accuracy is 81.2. So here we came to an end. So we'll be looking on further tutorials in the next week. So stay tuned. See you next week. Goodbye.